Hello, in this video, we'll discuss some problem-solving examples related to topics we have covered so far until Lecture 3. So before proceeding, we'll just review the equations we have introduced in Lecture 3. So first we have the Fermi function, in which we have to know the Fermi level and the temperature alongside with the energy of concern we're looking at, and we'll use this to compute the probability that the state is occupied or not by an electron. Also, we have this equation for intrinsic semiconductors under thermal equilibrium. So this one is the same as we had before. N is equal to P is equal to Ni. And now we can use this one, EF is equal to EI, for intrinsic semiconductors in thermal equilibrium. Now the side on the right, EI is equal to EC plus EV over 2, can also be used even if the material is not an intrinsic semiconductor or not in thermal equilibrium. We're just limiting it for the second bullet that if it is an intrinsic semiconductor and it is in thermal equilibrium, then EF is equal to EI. Next, we have these equations for non-degenerately doped semiconductors in thermal equilibrium. So first, when we say non-degenerately doped semiconductor, so we have this condition right here where EF must lie between EC and EV within a 3 kT margin. Now, given that that is true, we can use these two equations on the left where we can compute the electron and hole carrier concentrations given Ni, the temperature, and the relative the difference between the Fermi level and the intrinsic energy level. Now for N we have EF minus EI, but for P we have EI minus EF. Now we can actually also skip these two equations and just go right ahead and write N is equal to ND or P is equal to NA as applicable in our previous discussion. And also we can actually proceed with these equations right here, assuming that the material is non-degenerately doped, and then just verify afterwards that EF falls within the valid range for non-degenerately doped semiconductors. Now, aside from these equations, we have also defined that the kinetic energy for electrons is the energy of the electron minus EC, but for holes it is EC minus the energy of the hole. So the higher the electron above EC, the higher its kinetic energy, but for holes, the lower it is relative to EC, then the higher its kinetic energy. Okay, we'll proceed with the actual problem-solving examples. So for the first problem, we are given a piece of silicon that was doped with Na is 10 to the 16, and the temperature was changed such that Ni is equal to 10% of Na at thermal equilibrium. Given this, we are asked what is Ni, is the temperature for this case greater than or less than the room temperature, can we assume total ionization for this case, and determine N and P if possible. So first, we summarize here the information we obtained from the given. So we have silicon, the acceptor doping concentration, the statement that the temperature changed such that Ni is 10% of Na, and then that the material is in thermal equilibrium. So for the first question, determine Ni. However, we have this statement right here where Ni is 10% of Na and Na is 10 to the 16. So we'll be able to solve that Ni is equal to 10 to the 15. Next is the temperature, for this case greater than or less than room temperature. We note first that the material is silicon, and it is implied in the question that the temperature is unknown. Now, since Ni is 10 to the 15 as we have solved here, and we note that this value 10 to the 15 is greater than Ni for room temperature, which we should have remembered by now to be 10 raised to 10. Now, at what temperature will Ni be greater than 10 raised to 10? Then the answer to that is some temperature greater than 300 kelvins or room temperature. So for this question, the answer is greater than room temperature. Okay, so here we just note that we already um, deduced that the temperature is greater than 300 kelvins and computed that Ni is equal to 10 to the 15. Now, can we assume total ionization in this case? So recall that at room temperature, we are already allowed to assume that total ionization happens. So since we are dealing with some temperature greater than room temperature, then it would still be valid that the total ionization assumption can be used. So yes, the total ionization can still be assumed, since the higher the temperature, the more dopants are ionized. But if all dopants are already ionized at room temperature, then they would still be ionized at a temperature greater than 300 kelvins. So yes. Next, determine the N and P if possible. So note that for this question, we know that the material is in thermal equilibrium. We know Ni, which is different from 10 to the 10. It is actually 10 to the 15. But the temperature is unknown. So whenever we encounter a formula with kT, then we basically can't use that so far. So we can't use these equations because we don't know this term. And even so, EI minus EF or EF minus EI. So what can we do? We have introduced those equations for lecture 3. We can still use the equations we have from lectures 2 and 3. So here, nothing is said about ND, so we can just assume that ND is equal to 0, and we are certain that it is a p-type semiconductor, so we can start with P using the same equations as before. However, note that Na is not much greater than Ni, since we have Na is 10 to the 16 while Ni is 10 to the 15. So that is just 10% and not much larger. So we do not use P is approximately Na in this case, but instead we use the longer form of the equation. So Na minus Nd over 2 plus square root of Na minus Nd over 2 squared plus Ni squared. But since Nd is equal to 0, so we remove those terms, we'll be left with 10 to the 16 over 2 plus square root of 10 to the 16 over 2 squared plus Ni squared, which is 10 to the 15 squared. So using our handy calculators, we should be able to get this value that P is 1.01 times 10 to the 16. So note that it is a bit larger than um, a bit larger than the acceptor doping concentration, because aside from the acceptor dopants that are ionized, we still have this term here, Ni. So P is a bit larger than Na in this case. And then since we already know or have a value for P, then we can just use the law of mass action. We can use this since the material is in equilibrium. So N is equal to Ni squared over P. Ni squared is 10 to the 15 squared, while P is, as we have computed 1.01 times 10 to the 16, and we'll be able to get this value that N is equal to 9.902 times 10 to the 13. So we have actually already answered all the questions for the first problem. So we have computed Ni based on the statement that Ni is 10% of Na. It is in room temperature since Ni is greater than 10 to the 10. Since the temperature is greater than room temperature, then we can assume that total ionization happens or occurs. Then we computed N and P based on the long formulas from lecture 2, and then used law of mass action to determine the minority carrier concentration, which is N in this case. Okay, problem 2. So for problem 2, we have a uniformly doped silicon semiconductor, which is constructed such that the probability of finding an electron at EI is 70%. The material is maintained at room temperature and left at thermal equilibrium. So the questions we have to answer are determine the electron concentration, so that is N, determine the hole concentration P, and then draw the EBD with EI and EF. So again, we summarize first the information from the given. We have a uniformly doped silicon, room temperature, thermal equilibrium, the statement, the probability of finding an electron at EI is 70%, which we translate here as F of EI is equal to 70%. So the first question is determine the electron concentration N. Okay, so the main information that we have here is that f of e is equal to 70%. If we go back to the equation for the Fermi function, it actually relates the energy level with respect to EF. So using that, we can first determine how far is EI from EF. Some information first. Since we have silicon at room temperature, then we know that Ni is 10 to the 10 and Eg is 1.12. And then we will use this equation to compute N. So we already know Ni. We already know the temperature since it is at room temperature. Then the question is what is EF minus EI, but we'll use this equation here to determine EF minus EI. So the Fermi function is 1 over 1 plus E minus EF over KT, but in this case, the input to the Fermi function is EI. So we replace this E right here with EI, and then we already know KT, which should be 0.026 electron volts. Then we can solve for E raised to EI minus EF over KT. So isolating that term, we can get the reciprocal of both sides of this equation, then subtract 1 on the other side. So 1 over 70% minus 1, which is 3 over 7. However, the equation is uses e raised to ei minus ef minus ei, but we know ei minus ef. But this is just equivalent to putting it in the denominator here, and making it e raised to ei minus ef, and we already know its value, which is 3 over 7, and then ni is 10 to the 10, and so we should be able to now compute the n, which turns out to be 2.33 times 10 to the 10. So the next question, we determine the whole concentration, and we just note what information we have so far. So we already have this one, and we have already computed for n, but instead of using this equation, we can just proceed with the law of mass action, because that's much simpler or shorter. So P must be equal to Ni squared over N. We can use this equation since the material is in thermal equilibrium. So P is equal to 10 to the 10 squared over the computed value 2.33 times 10 raised to 10. And we should be able to get something less than 10 raised to 10, which is 4.286 times 10 to the 9. So we already have computed for P. Note that we can go the, say, longer way or harder way, and use this information. So Ni, which is 10 to the 10, times this value should still give us this P. Sorry, this whole thing should give us this value for P. Now, one thing we noticed that previously we used N is equal to Ni e raised to Ef minus Ei over Kt, which is only applicable when the material is non-degenerate. But we have not yet proven that it is non-degenerate. So we simply assume that the material is non-degenerate, then using this equation here, we can solve for Ef minus Ei, and that should be 0.22. And as we will show later, Ef turns out to fall within our range for non-degenerate semiconductors. So we can actually use this equation, or our assumption is correct, and we do not need to redo the calculations. So the next task is to draw the EBD with EI and EF. The first thing that we can draw is actually EC, EI, and EV. We know that the material is silicon at room temperature, so EG must be 1.12, EI must be in between, so the difference in energy levels is 1.12 over 2, which is 0.56 between EC and EI, and EI and EV. And then all we need to locate now is EF. So using the value we have computed, we use ln on both sides of this equation and end up with EI minus EF. So KT is moved from this point to this point, and then we'll multiply that with ln times, or ln of 3 over 7, but KT is 0.026 electron volts, and with that value we can compute EI minus EF is equal to negative 0.022 electron volts. Now since EI minus EF is negative, then that would mean that EF is actually above EI, or EF is equal to EI plus 0.022 electron volts. And that is also consistent with our previous results, that N is greater than P. So this is 10 to the 10 versus 10 raised to 9. So the material must be N-type, and therefore the Fermi level must be above EI. And so now we draw EF here at 0.022 electron volts above EI. So it is just slightly above EI. And with that, we have actually completed or finished problem 2. We have already solved N using N is equal to NIE raised to EF minus EI over KT. Then we solved the law of mass action. We solved P quickly using the law of mass action, and then using the values for either N or P, we can compute EF minus EI or EI minus EF. Then insert that into our energy band diagram. And again, remember that when the material is an N-type, the Fermi level must be above EI. Okay, last problem for this video. Answer the questions using the given EBD of a uniformly doped silicon sample at thermal equilibrium at room temperature. So we have this EBD. We are asked, is the material N-type or P-type? Is the material non-degenerately doped? Determine the electron and hole concentrations. Determine the probability of finding an electron with a kinetic energy of 10 milli-electron volts. So first, is the material N-type or P-type? So we have just said that when EF is above EI, then the material must be an N-type. Then next, is the material non-degenerately doped? So note that this value right here, 10 kT, is 260 milli-electron volts or 0.26 electron volts, since we are dealing with a room temperature problem. So KT is 0.026, multiply that by 10, you get 0.26. Now, the difference between EC and EF, which is here, must be equal to 1.12 over 2, which is 0.56, minus 10 kT right here to get this one. So 0.56 minus 0.26, and that is 0.3 electron volts. Now, given this information, is the material non-degenerately doped? So this margin, or this distance from EC, is actually greater than 3 kT. So the margin for non-degenerately doped is actually 3 kT. which is equal to 3 times 0.026, which is 0.078. And so since 0.078 is still smaller than this 0.3, then EF must be lying within the margin for non-degenerately doped semiconductor. So the answer is yes. The material must still be considered as non-degenerate. So next, determine the electron and hole carrier concentrations. Now that we have drawn the energy band diagram, we can use this to solve N and P, since the material is in thermal equilibrium, and that we have already proven that it is a non-degenerately doped semiconductor. Then we can use this equation here to solve for N, where Ni is equal to 10 raised to 10, since we have silicon at room temperature, and then times E raised to EF minus EI, which is 0.026, or 0.26 over KT, which is 0.026, and we should be able to enter that into our calculators and get 2.2 times 10 to the 14. Now we can use the same or the similar formula for P. So 10 raised to 10 times E raised to EI minus EF. But we have here in our energy band diagram that EF is above EI by 0.026. So EI minus EF must be negative 0.26 over 0.026, and solve that P is equal to 4.54 times 10 to the 5. However, again, the shortcut is to just use the law of mass action. So P is equal to Ni squared over N. And you're most likely to, or less likely to misuse that equation. So we have already have a value for N and P. So the next question, determine the probability of finding an electron with kinetic energy of 10 millielectron volts. The first thing we have to note is that this is a probability was mentioned, so we should be using somewhere in our solution the Fermi function. And the probability of finding an electron with a specific energy, not necessarily kinetic, is given by f of E. However, we have already described that the kinetic energy of an electron is its energy level minus EC, and since the kinetic energy is 10 millielectron volts or 0.01 electron volts, then this means that the electron must be above EC by 0.01 electron volts. Now, we can determine how far is that relative to EF, and then use the Fermi function. So 1 over 1 plus E raised to the energy of the electron minus EF over KT. But this E of the electron minus EF is 0.3 plus 0.01. So that's 0.31 over KT, so 0.026. And therefore, we can now compute. So the probability of finding an electron with that kinetic energy must be equal to 6.64 times 10 to the minus 6 unitless, or multiplying by 100, 0.000664%. So that is a very, or relatively, say, small probability since the electron energy level is a few kT above EF. So the probability must be very small. So to summarize, we have answered the question. So given this EBD, we can determine that it is N-type, that it is non-degenerate. We can also compute N and P since we know that the material is in thermal equilibrium and it is non-degenerate, so we can use the equations presented. And then we have also computed the probability of finding an electron with kinetic energy of 10 millielectron volts. So the key to this one is to identify first in the energy band diagram where the electron lies, and then use the Fermi function. Okay, so that's it for the problem solving for lecture 3. If you're interested, you can check past EEE 41 DC slides or problem set or exam. And if you have any question regarding those, then please post your questions in Piazza. Thank you very much.